So hello everyone and welcome to this video, which is part of a series of videos that I'm making about the topic of geometry, which will be very relevant for a lot of aptitude-based entrance examinations like CAT and GRE. The intent of this series is to provide some very basic conceptual understanding of the foundations of the topic of geometry. And today we are going to be looking at a particular concept called reflection. Although reflection directly cannot be used to solve questions. But since geometry is about so many different theorems and formula and concepts, and people constantly mug these up and they try to apply that in the examination, and a lot of times they don't know where to apply, what to apply. So I'm going to be discussing this very fundamental concept of reflection, which is the basis of a lot of theories in geometry. If we can understand reflection, if we can visualize reflection, we will not forget a lot of these very basic theorems and concepts in geometry. So a lot of times, at the time of the examination, at the time of solving questions, people cannot exactly recollect what the relationship is and how to apply them and where to apply them. But if we can visualize, if our visual thinking can become better, then automatically our capability to solve questions become better. So let's understand what is reflection first. See, reflection is something that happens in the mirror, right? And we have to remember that if the reflecting surface is a linear surface or a point surface, then the object that is getting reflected and the image that it creates after reflection are going to be identical to each other. So if you are standing in front of a flat mirror, then your reflection will be absolutely identical to you. Some kind of inversion might happen, but otherwise the image and the object are going to be identical. And using this concept, a lot of equalities in geometry-based concept can be explained. So let me divide reflections into two types. And those two types are, number one is point reflection. So in point reflection, what happens is there is going to be a point, a singular point, which is going to become my mirror. And I'm going to be reflecting things about it. And I'll give you an example. Let's suppose I have a blue point here. Let me call this blue point A. So if I want to find the reflection of this point A about the mirror M, then what I need to essentially do is that if I join the blue point A and the mirror M, and if I produce the straight line, the line segment AM on the opposite side of M in the same direction, equally to the distance of AM. So the distance of AM, I'm going to be reflecting it, or I'm going to be producing it from M in the same direction, equal to the distance of AM. Then the point that I will end up with on the other side, A dash, is going to be the reflection of A. This is how point reflection works. Similarly, let's say that I've got another point B on one side of it. Then again, the reflection of point B will be, again, I will draw a straight line from B to M. And I will produce a straight line in the same direction on the opposite side of M, equal to the distance of BM. So when this happens, then the point that I end up with on the opposite side of M, this will become B dash. So then B's reflection is B dash, which means that if I have a straight line, a line segment rather, AB, and if I reflect every point on this line segment about the point M, then I will end up with the line segment A dash B dash. And if you can visualize this properly, of course, I've not drawn it very accurately, the reflection accurately, but if you can visualize this properly, you will realize that these two line segments, A dash, B dash, and AB, are not only identical, are not only equal in length, but they are also going to be parallel to each other. This is called point reflection. Now let's understand the second type of reflection, which is slightly different from point reflection, which is a line reflection. So how is the line reflection different? In line reflection, what we do is that instead of having a singular point as a mirror, we'll have a straight line as a mirror. Let me call the straight line M. So if I have to reflect, let's say, this point A about this mirror M, then what I'll do is from this point A, call this point A, from this point A, if I drop a perpendicular on the mirror M, okay, so this is going to be a perpendicular. And if I produce this perpendicular on the other side of M, at a length equal to AM, then it might lead me to this red point, which is A dash. And A dash will be the reflection of A. Similarly, again, let me take another point, another blue point on the left-hand side, B, which is the object. To reflect B about the mirror M, again, I will drop a perpendicular from B onto M, and I produce it on the opposite direction, equal to the distance between B and M. And then that will lead me to this red point B dash, and B dash becomes a reflection of B. Which means once again, if I have a blue line segment AB, it reflects about this line mirror M, and it becomes, I think I drew this a bit farther away than it should be. I think the length of B dash should be slightly lesser. Yeah, that does justice to it. Let me erase this as well. This looks more like the location of B dash. So if I join A dash B dash, then A dash B dash is a line segment which is a reflection of the line segment AB. Now the thing to note here is that although AB and A dash B dash are identical to each other in terms of length, but they are not going to be parallel to each other, as is the case of point reflection. Here, what happens is that AB and A dash B dash are converging on the top side and diverging on the bottom side. So that's why line reflection and point reflection are slightly different. And if we can understand the perpendicularity of the nature of reflection when it comes to line reflection and point reflection being only through a point, then these two put together can help explain several fundamental properties that we learn in geometry. Let me give an example. A very, very basic concept that I think all of us should be aware of from our high school itself in terms of geometry is that vertically opposite angles are equal. What's the meaning of vertically opposite angles? It means that if I have got two lines which are intersecting each other at a point, let me call these two lines AB and CD, which are intersecting at O, then I know that angle AOD and angle BOC are equal. Now, why are they equal? Because imagine if this point O was a mirror, then A's reflection will lie somewhere along AB on the opposite side of O. D's reflection about O will lie somewhere on the opposite side of O near C. So which means that this angle AOD's line reflection will become this angle BOD's reflection. This angle AOD's reflection becomes a point reflection, or it's the point reflection becomes this angle BOD. That's why vertically opposite angles are equal. Similarly, angle AOC's point reflection about O becomes angle BOD, and that's why they are equal. Now, let me also show you how line reflection can help explain a lot of concepts. Let's say we have a parallel line and transverse system. I think that all of us know what parallel lines are. If AB and CD are parallel, that means that they will never intersect each other. They will never touch each other, no matter how far we extend these two lines on either side. And suppose there is a transverse. A transverse is a straight line that intersects a set of parallel lines. If I call this transverse EF, and let's say it intersects AB and CD at G and H respectively, then we know from our school life that corresponding angles are equal. Now, what is the meaning of corresponding angles? An example of a pair of corresponding angles in this figure are angle EGB and angle GHD. These two are equal. Now, why are they equal? They are equal because, let me explain. Let's say that at the midpoint of GH, I have a point M. Okay. And if I reflect B about M, let's say I reflect B about M, then B's reflection, B dash will lie somewhere in the same straight line as CD. G's reflection will lie at H. Right? And M's reflection will be M. So which means, or G's reflection will be H, E's reflection will be somewhere along F. Right? So B's reflection is here, G's reflection is at H, E's reflection is at F. So angle EGB and angle B dash HF will become equal. So if EGB and B dash HF are equal, then B dash HF and GHD are a pair of vertically opposite angles, which I've already proven through point reflection to be equal. So that's why all these three angles will be equal. So if I remove this, then that means that angle EGB and angle GHD are equal. So corresponding angles are equal can also be proved using point reflection. It's just going to be point reflection about M and then point reflection about H. So this is how point reflection can help us figure out a lot of basic concepts in geometry. In the same fashion, if we have an equilateral triangle, several times you would have heard people say that if it's just an equilateral triangle in which all three sides are equal, AB, BC, and AC are equal, all three angles are equal, angle A, angle B, angle C, all are equal to 60 degrees. Then if we drop a perpendicular, okay, or if we join, not perpendicular, let's say that if I join A to the midpoint of BC, if I call it D, then AD will be perpendicular to BC. Now, why will they be perpendicular? How can we prove that AD will be perpendicular to BC? That AD will be the height of this triangle. AD will be the interior angle bisector of angle A. How can you prove that? It's again basic concept of line reflection. If D is the midpoint of BC, then if I take this straight line AD as a mirror, then B's reflection will be at C, A's reflection will be at A, D's reflection will be at D. Which means that this left-hand side triangle, triangle ABD, will be identical to the right-hand side triangle ACD because line reflection does not change the proportions of objects. That is why angle BAD and angle CAD will be equal. That is why AD becomes the interior angle bisector as well as the median of this triangle. Also, we know all the angles are equal to 60 degrees, so which means that this angle becomes 30, this angle becomes 30, this angle becomes 60, this angle becomes 60. So the third angle of both these triangles have to be a 90-degree angle because the sum of all three angles of all triangles is 180 degrees. That is why the median of an equilateral triangle will also be its altitude. It will be the perpendicular drawn from one vertex onto the opposite side. So line reflection can help explain why the altitude, the interior angle bisector, and the median are all the same straight line when it comes to an equilateral triangle. Several basic concepts in geometry that deals with equality of lengths, equality of angles, revolve around the concept of reflection. If while looking at a figure, we can visually see that there is a point of reflection, there is an axis of symmetry, then a lot of concepts that are present in geometry, we can figure out that, oh, these can be applied in the question. And that immediately elevates our capability to solve problems. So this video was all about reflection. We'll move forward in the series and we will talk about several more fundamental concepts, their applications and their derivations, and what kind of questions can we solve using those basic concepts. So stay tuned for more. Thank you.